Another advantage of organizing functions into families is that when we meet a family of functions, they will typically have similarly structured domains and ranges. So when we're learning about a family of functions, one of the questions we'll ask is, what are their domains? What are their ranges? And the domain of an absolute value function is easy. The domain of the base absolute value function is all real numbers, right? The way that we defined the absolute value, we can take the absolute value of any real number. Composing with linear functions doesn't change the domain. So the domain of any absolute value function is all real numbers. The range is a little bit more challenging because the base absolute value function does not have a range of all real numbers. The absolute value is always either a positive number or zero. So the absolute value function has a range consisting of all positive numbers that's most easily written in interval notation as the interval 0 to positive infinity. And 0 is possible, right? The absolute value of 0 is 0. So we have a closed bracket there. What about in general then? How do we figure out the range in general? Well, the easiest way to figure out the range for a new type of function, once we know what its graph looks like, is to just consider the graph. So here we have a kind of generic absolute value function. F of x is a third times x plus 1 minus 1. So we're going to start by finding the point of the v, and that happens where x plus 1 is 0. So at x is negative 1. We're going to put that in the middle of our table. Then the denominator of our fraction is 3. So we're going to find a point to the left by subtracting 3. We're going to find a point to the right by adding 3. Negative 1 minus 3 is negative 4. Negative 1 plus 3 is positive 2. And so we'll have 1/3 absolute value x plus 1 minus 1. And we'll plug in x is negative 4. So that'll be 1/3 absolute value negative 3 minus 1. Absolute value negative 3 is 3. A third times 3 is 1. So we'll just have 1 minus 1 is 0. A third absolute value negative 1 plus 1 minus 1. So negative 1 plus 1 is 0. A third times 0 minus 1. So that's just 0 minus 1 is negative 1. And finally, a third times absolute value 2 plus 1 minus 1. So that's a third times absolute value 3 minus 1. A third times 3 is just 1 minus 1 is 0 again. And there's something I want to call your attention to about this calculation here. This absolute value part is 0 by design, right? That's why we chose x equals negative 1. So we chose x equals negative 1 so that at the point of the v, our output would be just this part. We chose negative 1 so that when we plug it in, this term would vanish. And all that's left is this number that's added or subtracted outside the absolute value. And let's see how that works out on the graph. We have negative 1 as the point of our v. And then we have -4, 0, +2, 0. And so our graph will look something like this. In this case, the V shape opens upward. And if we go ahead and squish this into the y-axis, we have a bottom here. And then if we were to continue to extend this graph, it would just continue all the way up. So our range here has a bottom at -1 and then goes up to positive infinity. So what do we see when we look at the graph? We see a V shape. Well, our V shape is going to either open up or open down. And what makes the difference is the number we multiply by on the outside. If it's positive, the V shape opens up. And so the range, noting that this first term is always going to be 0 at the bottom of a V shape opening up or the top of a V shape opening down, the range is just this number and everything greater than it. So the range is just d to infinity. If a is negative, then we have a V shape that opens down. And the range is going to consist of everything under this same number. So if we have a V shape that opens down, the range is just negative infinity up to d. And if you forget that, that's okay. You can just sketch the graph and see what the range looks like. This isn't something that you have to memorize as just a random fact. It's something that's linked very strongly to the shape of this function.